Okay, we have here today the sum from n equals 1 to infinity of 1 over 6n plus 2 minus 1 over 6n plus 3. And I have some crazy methods I want to try on this one. I haven't even tried to figure out if any of these are worthwhile. I think there's probably a lot of extra steps in here, so don't look at it from the standpoint of trying to be efficient. I think there's going to be faster ways. So for my first step on, I just want to notice that we've got this 6 on the n in both cases. So what I'm going to do is let's just factor out a 1/6 from this. So when I do that, what we're left with, the first one's gonna become 1 over n plus 1/3, and the second one is gonna be just n plus 1/2 over here. And now here, you may notice that with just a slight rearrangement, you could actually go to the Digamma function right now. I don't know if that's the fastest way, but that's faster than what I'm gonna do right now, which is I wanna try to use a Laplace transform on this. I wanna look at each of these as the Laplace transform in n. Now the other way we've done this in the past is with an integral, so it's kind of similar to that, but instead we're going to use the Laplace transform on this. So what we can do for this first one, this is in the right form for a Laplace transform with the base of e. So it would be like if we have e to the minus 1 over 3t, we usually take our Laplace transform in s, but I'll do it in n just to get it to match what we have here. Well, our formula for this, if we wanted the Laplace of e to the at, this is just going to be the same thing as 1 over s minus a. So if our a value is minus 1/3, what we're going to get here is just 1 over n plus 1/3. So this is going to give us an expression for this first piece right here. Then I'll do the same kind of thing on this one. We can do e minus 1/2 t. And then for this one, it's just going to give us 1 over n plus 1/2. So we can take each of these and put it back into our sum, but what I'm going to do is let's use the definition of the Laplace transform to save a step. So we'll write each of these in terms of an integral. And so what I did to save space, I just put it all under one integral sign, bringing them together. But we have our e minus 1/3 t here and our e minus 1/2 t here. And then next, let's just swap the order of the sum and the integration. And now for this sum here, we really have got the same thing going on for each of these. So what we can do, let's kind of break it out separately. Let's just look at one. We'll kind of just do this general case over here. We'll look at e minus nt, and then this other piece, let's call e minus at, where like a is 1/3 here and 1/2 here. Well, this term's a constant with respect to the series. There's no n in it, so we can bring this out front. We'll have e minus at, then we'll have our sum. For this, I want to write this just a little differently. Let's write it as e minus t all to the n with exponent properties. But then this here is almost our geometric series formula. There's a few differences. For geometric series, we're usually starting at n equals 0, and this is going to be x to the n, where absolute value of x is less than 1. So in this right here, the x value is going to be this e minus t. There's not going to be a problem. The convergence is going to be fine because we've got positive values here, negative exponents, so these values are all going to be between 0 and 1. So that part is going to work. Now for this case right here, we have the formula. This is the same thing as 1 over 1 minus x. But if you change the bound, if you change the lower limit to 1, then we can just take the first term. And so then if you plug a 1 in, the first term is going to be an x, so we can write it like this. So then using our formula, what we have here, we're going to have e minus at in front. This is going to become 1 minus, our input here, e minus t, and then we're just going to have e minus t in the numerator. And then we could combine these terms here because we've got the same base, but I think I'm going to leave it because then we can factor it out later, because remember we've got two of these going on. So let's use this and we'll plug it back into our integral over here. But now here we can get quite a bit of simplification. We've got the same denominator here, so we can combine these fractions, and we've got this e minus t in common that I can factor out. So when I do this, let's see, we'll put it all over one common denominator, 1 minus e minus t. I'll factor the e minus t out and put it to the end, and so then we'll have these two terms left in the numerator. We'll have e minus 1/3 t minus e minus 1/2 t. Now just one more thing on this. Notice if I multiply in a minus sign here, we're going to be setting up a u substitution, and then so I don't change it, let's just reverse the sign on this right here. And so then for the u substitution, I just want to do it on e minus t. So I'll set u equal to e minus t. And then when you take a derivative on that, du is going to be minus e minus t dt. So let's go ahead and substitute. We have our 1 over 6 in front. Plugging in infinity here, that's going to 0. plug in 0, e to the 0 is just 1. Then in the denominator, it's just going to become 1 minus u. We'll reverse this because we flip the sign. So I can write like e minus 1/2 t. That's the same thing as e minus t to the 1/2. So for this right here, I can write this as u 1/2, and then this one will be u minus u 1/3. And then again, all this stuff is just du. And actually, I shouldn't have flipped the sign because I want to flip it back. So that's going to be another unnecessary step right there. But let's flip the sign back, and then we'll bring a minus sign up front that we'll use to flip the bounds. And I'll just reorder this again. But now for this integral here, I've got a formula we can use. Let me clean up the board and we'll work on this integral. Okay, so now for this integral, what I have over here, these two formulas here are actually identical. I just changed the input, right? So the first one we're inputting z, and the second one we're inputting t, and we get back something in terms of the Digamma function. But then if I just subtract these two integrals, what I get here, this is exactly in the form of our integral up here, two different inputs where we have 1/3 and 1/2. And then we get something else in terms of the Digamma function, but we've eliminated the Euler-Mascheroni constant that we have right here. So if you remember it, you could just skip to this last formula here, but the way I kind of remember it with these formulas, and then I just subtract them to get back to this, so either way. So in our integral, using this formula here, the t value on this is going to be 1/3, and the z value is going to be 1/2. So to simplify this, we can go to this formula right here. We're going to have 1/6 in front, and then we're going to have, this is going to be digamma of z plus 1. Digamma of z plus 1 is going to be this value plus 1, so this is going to be digamma 3/2. Then digamma of t plus 1, this is going to become digamma of 4/3. Then for each of these, let's reduce it. I have this formula. We have this recursion formula for the Digamma function. If we have Digamma z plus 1, we can reduce it by 1 to Digamma of z plus 1 over z. So using this on Digamma of 3/2, we get Digamma of 1/2, flip it, plus a 2. Doing the same kind of thing on Digamma of 4/3. This is going to become Digamma of 1/3, flip it, plus 3. So we use these values to go ahead and reduce this. We've got our 1/6 in front here. This is going to become Digamma 3/2. We're going to have Digamma 1/2 plus 2. Then minus this value, which is Digamma 1/3, distributing the minus sign, minus 3. But then for each of these values, I did these in previous videos, so I'll give you a link to the Digamma playlist where we derived each of these. But let's just use those values. So plugging each of these in, first we'll have Digamma of 1/2, so that's going to be minus 2, ln2 minus Euler-Mascheroni constant. 2 minus 3, that's going to be minus 1, putting that together, minus Digamma 1/3. I'll distribute a minus sign into all this stuff, so we'll have plus pi over 2 square root of 3 plus 3 ln 3 over 2, and this becomes plus Euler-Mascheroni constant. I'll put it all over 6, but Euler-Mascheroni constants are going to cancel. And then from here I could divide into 6, but maybe let's actually factor out a 1/2 from everything. Maybe that's going to look better. I don't really know. So if I factor out 1/6 and 1/2 from everything, we have 1/12 in front. Then let's go out of order. This one, if I factor out the 1/2, this is just 3 ln 3. This one's just going to be positive pi over square root of 3. This becomes a minus 2. This becomes a minus 4 ln 2, and that's it. Okay, so there you go. Really interesting method. Not sure which parts of it were necessary. Maybe none of it was necessary. I could have just skipped the whole video, right? But anyway, I don't know. So I just like to explore the methods. So that's it for today. Thanks everyone for watching. Have a good day.